Welcome, everyone, to NTIA's workshop on lunar propagation. I'm thrilled to have everyone join us today for what we're hoping will be a very exciting discussion on lunar propagation. As we return to the moon, it's really important that we understand the lunar propagation for communications to ensure, because it's going to be very different than what we have here on the Earth. So just to walk you through our agenda today. After I walk through our agenda and some logistics, I'm going to turn the floor over to Sarah Morris, who's our Deputy Assistant Secretary at NTIA. And then we'll have a presentation by Billy Kozma from the Institute of Telecommunications Services, which will set the framework for our panel discussion, which will be moderated by Whitney Lohmeyer of the FCC. With that, I wanted to make sure that everyone knew that if you have a question, you should please use the Q&A function at the bottom of your screen. And we'd ask when you put your question in, if you could also identify yourself and your affiliation. I think that will make it even easier for our panelists to be able to respond. So I think this is going to be a great event. I'm really excited to hear what everyone has to say. And now I'm going to introduce Sarah Morris, our Deputy Assistant Secretary at NTIA, so she can give some remarks. Over to you, Sarah, and thank you.
Thank you, Jennifer, for the introduction. Good morning, everyone, and welcome to this virtual workshop, which is addressing a key and I think really fascinating topic that serves as a critical reminder of just how far-reaching our technological innovation has become. Yes, we're talking about the spectrum environment on the moon. Who'da thunk it? And we are talking about it not as something far off in time or imagination, but as a prerequisite to expanding our footprint there in the very near future. The United States is already leading the way in bringing men, and very soon the first woman, to the moon in a quest to advance discovery and innovation and prepare for expeditions deeper and deeper into space, including human missions to Mars. Without getting too lofty, these efforts present a real opportunity to deepen our understanding of our planet, our solar system, and to figure out how to live, work, explore, and create in a totally different world. Importantly, these missions will enhance our competitiveness right here at home. They can spearhead new launch capabilities, which benefit just about everyone interested in commercial space. They can create new jobs and new investment, supporting billions in additional economic output. They can spin off new technologies with terrestrial applications, as space exploration so often does. They can also help us build and sustain a pipeline of U.S. technical workers who are talented, well-paid, and fully equipped to succeed at technology's leading edge. Of course, we aren't the only country advancing this work. The moon has become an increasingly popular destination for other countries as well. And whether you're in the United States or another spacefaring nation, radio communication will be essential to the success of our lunar ambitions, just as it has been to our achievements on Earth. That's why we're all here. Given the importance of wireless communication to space exploration and growing interest in activity in and around the moon, we need to get better at deconflicting the use of radio frequencies allocated for use in lunar missions. To do that effectively, we need to know how strong radio signals are going to be in any given use case. That, in turn, requires a viable propagation model. Because of its lack of an atmosphere and unique mix of materials and topography, the moon offers us new lessons in complexity that make it important to explore new ways to model propagation. And as a pioneering spacefaring nation, the United States has been working hard to drive progress in this effort. Communication Conference is to make spectrum allocations for future development of lunar and cislunar communications. I think I froze. If folks can hear me now. Okay, I'm back, it looks like. So this workshop will serve as a benchmark in surveying the progress we already have made on developing lunar propagation models, and as a call to advance that progress in the United States and at the ITU. Indeed, one of the key agenda items at the ITU's 2027 World Radio Communication Conference is to make spectrum allocations for future development of lunar and cislunar communications. Together, we will explore the technical and scientific issues and challenges, as well as the work that's going on already at NTIA's Institute for Telecommunication Sciences, or ITS, elsewhere in the federal government, and in ITU study groups, including in preparation for the next WRC. So thank you once again to our participants and attendees. This is a critical forum for these conversations. And with that, I will turn it back to Jennifer, with apologies for the communication freeze.
And thank you so much, Sarah. And hopefully when we get to the moon, we won't have these blips. So thank you so much for your inspiring remarks. I think that's a great kickoff to our event today. And now I'm going to pass the mic over to my colleague, Billy Kozma from the Institute of Telecommunication Sciences at NTIA. Billy is going to lay the framework for our discussion today. So Billy, over to you, and thank you.
Thank you very much, Jennifer. So I have welcome everyone. I have a couple slides to go over before we get to the meat of this event, which is the panel, to lay down just some basics and some understanding of lunar propagation as we're working here, both within ITS and within the nation as a whole. So I'm going to go over a few terminology, some of which I'll use in myself, some of which will be used in the panel, some aspects, overview of propagation on the lunar surface, something that we are working on within US Study Group 3 and internationally, the irregular lunar model, and then some links to some software and data that's out there if you're interested in engaging and participating or just following the work going on, where you can go. So some quick terminology, and I know there's a lot of text here. Most of you are probably familiar with basic transmission loss, right? That's the loss between two isotropic antennas, generally in dB. You heard Sarah mention the word cislunar. For those of you who don't know what that term means, that's propagation between the Earth and the Moon. We have the lunar regolith, and that's a term you'll hear throughout this conversation. The regolith is the lunar surface. However, it is unique in relative to the Earth, as we generally think of terrain, both because of its mineral composition and also its stratification and layering that's involved there. And so it adds some unique aspects to propagation when we think about it. We have terms like transhorizon, which most of you probably know. That's talking about that array going from one antenna to another is obstructed by, in this case, the surface of the moon. We have diffraction, which is essentially the propagation of radio rings around the edges of surfaces. And we really generally have two types of diffraction we can consider and think about on the moon. We have smooth sphere diffraction, in which is you have obstructions due to the curvature of the moon. So you're beyond the horizon, and that bulge of the moon is obstructing that direct communication between two antennas. Or you have knife edge diffraction, which is essentially irregular obstructions that are on that smooth sphere, that obstruction that are blocking the propagation. And of course, we have troposcatter. Those of you familiar with interference analysis and those sorts of aspects are familiar with the term troposcatter. It's the forward scattering of electromagnetic waves due to the behavior and the composition of the atmosphere. So when we think about propagation on the lunar surface, there's a lot of use cases that are being developed on how this is going to be used, right? So one of the things that's in particular unique about the lunar surface is there really is a lack of an atmosphere on it. And this changes our approach to modeling that we traditionally use within on Earth. So this means that things such as troposcatter that I just talked about from the atmosphere, because a lot of water vapor dominates a lot of that, it doesn't necessarily apply when we talk about this. So what we're left with is what amounts to free space propagation when there is no obstruction between your two antennas, and you have reflections and scatterings. And I know the panelists are going to talk about that and tools to kind of think about what that means for communication. And then you have beyond the horizon communication, which is dominated by diffraction. That's knife edge and smooth sphere that I talked about. There is no transition into troposcatter that we generally see on the Earth. One of the other things we have to think about is variability. So there's multiple ways we think about signal variability because it's a random process on the Earth's surface. On the moon, it's a little bit different on how we think about it. You know, things such as time variability due to our weather and meteorological phenomenon don't exist, but we do still have variability in the sense of changes in location and the irregular surface of the moon. And so we need to think about this holistically and have a full distribution Sometimes we think about one side of the distribution due to coverage. We want to be able to provide coverage, say we're talking from a lunar base to a rover at some 0.9% of the time. And sometimes we need to think about interference because the uses of the moon are quite varied and they include radio astronomy. And we want to protect certain assets in some places while communicating with others. So we need to still think not just about median losses, about a distribution of signal strengths over areas. And of course, as I mentioned, the lunar regolith is complex. There's unique mineral compositions on there. There's stratification and layering, which I think will be talked about in the panel. And these things need to be considered when we talk about propagations, in particular, some of that beyond the horizon, and how we model those, because they are unique and different than what we consider here when we talk about terrestrial propagation. So all of this is being actively developed. So in FY24, US Study Group 3 did provide some responses to a liaison statement, as Jennifer mentioned and Sarah, that there is work being done at the international aspect on a study question. And we provided some response as well as some software and what we dubbed the irregular lunar model. So those of you familiar with the ITS irregular terrain model, or Longley-Rice as it's sometimes called, we adapted that to the lunar surface and we presented that forward to Study Group 3 at the international meetings. And that was kind of adopted and modified and provided as initial response liaison statement on that question. So it generally has two modes of propagation, a point-to-point and kind of a coverage mode if you're thinking about an area and you want to provide certain levels of service to that. We did some initial analysis of the lunar surface. There are lunar topography models out there that we can generate and do some statistical analysis of that and how that affects, and we can adapt our models to the lunar surface, the ones that were developed from Earth. And as I mentioned, for those of you familiar with ITM, things like troposcatter has been removed, things such as time variability due to meteorological conditions have been removed. So the model has been modified to adapt itself to the lunar surface. Because for those of you who are familiar, ITM is fundamentally based on a physics-based model. And so while the environment is different, the underlying physics that dominate and electromagnetics that dominate propagation still reside on the surface of the moon. So all of this, I'll kind of wrap up here. We do have our software implementation. It's still being worked a bit. You can go to that public GitHub link. I encourage you to go out. You can see the source code. It's in C++. If you want to engage, provide comment, please reach out. There's lunar elevation data. There's a link there to go get that. And you can pull profile information or statistics of the terrain to feed into that and see how this works. On that page, you'll see readmes on how you kind of think of what these parameters are and how you can apply this model to the lunar surface. And so with that, hopefully that gives a kind of broad contours of the outlook of what we're talking about propagation. And with that, I'll turn it back over to Jennifer at conclusion. Thanks.
Thanks so much, Billy. We appreciate that. And I just wanted to remind folks, we do have Q's and A's available in the chat if you want to type one in. And Billy will be around to answer questions on his presentation when our moderator opens the floor later for Q's and A's. So please feel free to add some to the chat if you have any. With that, I wanted to turn the floor next over after Billy's great presentation laying our framework to Dr. Whitney Lohmeyer of the Federal Communications Commission. Whitney has a team of experts who are going to join her on this panel to discuss further issues on lunar propagation. So with that, Whitney, I'd like to turn the floor over to you, please.
Thanks so much, Jennifer. And also welcome my panelists to come on in video. But like Jennifer mentioned, my name is Whitney Lohmeyer. I'm Chief Technologist of the Space Bureau, and we focus on all things to do with spectrum and licensing and innovation for our commercial satellite industry. We work closely with our federal partners, and so it's a pleasure here to be able to moderate this panel. And to kick it off, we're going to do some introductions. So I'm going to have each of our panelists introduce themselves, share with us where they're working and what sort of interesting projects pertaining to lunar communications they're involved in currently. So Mike, would it be possible to have your video on? Could we hear from you first?
Yes. Sure, thank you. Can everybody hear me okay?
Yes.
Okay. So hi, I'm Mike Zemba. I'm at NASA Glenn Research Center in Cleveland. I've been involved with atmospheric propagation in the ITU going back to about 2011. And more recently, the focus on the lunar propagation effort. So I'm the principal investigator for a project we have at Glenn called Lunar Surface Propagation, which is our main interface from NASA to engage with this propagation work in the ITU, and then also understand how we can apply real data from the lunar surface to validation of models like this, and just improve our understanding overall of the lunar surface propagation environment.
Thank you so much, Mike. Greg, could we hear from you next? Who are you? Where are you working? And how are you involved in lunar technology?
Absolutely. Thank you, Dr. Lohmeyer. First, I'd like to thank the NTIA for inviting us. I'm Greg Skidmore at REMCOM. We are a small US owned and operated business up in near Penn State, in State College, Pennsylvania. We've been doing propagation for a very long time. Everything we do is focused on EM modeling and simulation. So it's either things like cell phone design, antenna design, radars, or propagation, and doing simulations for it. And we are very fortunate at the moment to have an SBIR with NASA, and we are developing wireless channel simulation and coverage analysis for lunar environments. So we are also developing models. We're very focused on the channel, the multipath. We're looking at this in a 3D sense, and we're also trying to tackle a lot of the same kinds of things, I think, in terms of this very challenging and new environment. We do this obviously for a living, but we also are very excited and passionate about this. That's what we do. And so we're finding this very enjoyable too. So we're very thankful for NASA to be including this, for all the researchers in academia that we're getting to work with, and for being allowed to participate in this panel. So thank you very much for having us.
Thank you. Next up, how about FCC? Chris, would you mind introducing yourself?
Thanks. Hi, everybody. I'm Chris Crisanthu, and I'd like to thank first the NTIA for giving me the opportunity to participate in this panel. As Dr. Lohmeyer said, I'm with FCC under the OET, the Office of Engineering and Technology, that we have a branch there that we are looking to different propagation modeling that we're using for different analyses. So as part of that, lately we start to looking also to lunar propagation, the effects, the difference between the lunar and terrestrial characteristics. And on the other side, also my background is with RF. It started long time ago while I was in the university. Working with my advisor was Dr. Bertoni, and work with Dr. Bertoni in various projects when I was in the industry and in DoD environments.
Thank you. And last but not least, Dr. Anderson from ITS NTIA. Can you give us an intro of yourself?
Sure. So I'm Chris Anderson. I am the Theory Division Chief for NTIA Institute for Telecommunication Sciences. I joined ITS in 2023 after spending 16 years as a professor of electrical engineering at the United States Naval Academy in Annapolis, Maryland. And in the Theory Division, our focus is on propagation modeling and interference analysis. That's the two key focuses or focus areas. There we go. Of the Theory Division. And our efforts are on using fundamental formal mathematical methods and rigorous physics-based approaches to develop accurate and high fidelity propagation and interference models for the kind of spectrum studies, propagation studies, interference analyses, supporting things like communications on the surface of the moon.
Thank you very much. So I just want to pause. Thank you all to the panelists. It's quite impressive that we have over 100 people on this call, and incredibly exciting to have such a crowd given such a niche and technical topic. And so to start us off, we've heard a little bit about propagation modeling in general from Bill's slides. I'm really curious to hear about the challenges with these sorts of models, and also whether industry is seeing something different than our federal entities. And so the first question is really, what are the biggest challenges in developing these models, and how are we addressing those? So Chris Anderson, would you mind kicking us off with your thoughts on this?
Sure. So I've spent most of my career as what I would call an empirical modeler. So starting with data, and it's a lot easier to get data from environments and locations here on the Earth than it is from the moon for obvious reasons. And the data not only for developing models but for validating models, right? So it's we can start with the physics, we can start with the theory, but at the end of the day, you've got to compare that theory against some kind of ground truth measurement, and so that's certainly a challenge. The other thing that's interesting is the models that we've used classically, the irregular terrain model, now the irregular lunar model, and other variations thereof tend to be 2D models, right? And Greg mentioned multipath. And I think understanding multipath and multipath propagation in an environment like the moon is going to be extremely important. And how do we incorporate that into models going forward is going to be an interesting challenge. So I'll pause there and let the other panelists weigh in.
Thank you. Anyone else have thoughts to contribute?
Sure, I can maybe piggyback on that and just talk. As Dr. Anderson mentioned, it obviously is very difficult to get data from the moon, but I can mention a couple of the opportunities that we've had so far, and a few of the opportunities that we have coming up that we're looking forward to being able to use to validate and continue to improve our modeling efforts. So for anyone who's been following lunar activity, which I assume is a good number of the people on the call, back in February, you're probably familiar that Intuitive Machines was successful in landing their Nova C lander on the lunar surface near the South Pole. So that was the first US mission to land on the moon since the Apollo days. And it was our first real opportunity to get our hands on some data. So they were, it was kind of a unique case in that they landed off nominally. So they came down and they had issues with their LiDAR system. So they didn't have good altimeter measurements as they were landing. So they hit harder than they expected. They ended up breaking one of the landing legs and then tipped over, but otherwise the craft survived. So they were able to get data back, but they were in this very off nominal position where they couldn't point their high gain antenna. And they had to essentially, communicate entirely over their omni antennas with a lot of reflections off the surface. So there's some great analysis going on right now of that data and the multipath effects that we're able to observe from that, both at NASA JPL and Intuitive Machines. So we're very much looking forward to how that can influence future multipath modeling in addition to the ILM model. And then the follow-up to that mission, Intuitive Machines 2, is actually planning to have a rover from a company called Lunar Outpost, and NASA funded we call it a tipping point demonstration, but it's we funded Nokia to deploy a 4G LTE system on that rover. So we'll be able to actually, the rover will drive around and collect performance data over the LTE link as the rover moves, ideally out to about 2 kilometers is the range we're expecting for that. And then that mission also has what they call the Micronova hopper on board Nova C. And so that's kind of a miniaturized version of the lander that's going to deploy and then jump around to different locations on the surface. And as long as everything goes well, jump down into a crater where it doesn't have line of sight. And that hopper also has an LTE UE on it as well. So we'll be able to collect data from that. So that's going to be our first really good validation opportunity for the ILM, I think.
Exciting. Greg, do you have thoughts on challenges, and are they different, being that you're private sector?
Yeah, we we have a long experience working also with the U.S. government, DoD contracts, and also the private sector and industry. So we do look a lot at 3D multipath on the Earth for terrestrial applications, whether it's indoor and urban areas, and we've often approached that with a different technique called ray tracing that's very 3D in nature. So one of the big challenges that we see in modeling this is that we do see a lot of 3D aspects to this when you get down into craters. For example, you may have a lot of multipath that's going out of a vertical plane to the sides, and the ridge lines, without the kind of erosion that we have on the Earth, we've got very sharp ridge lines and a lot of rugged terrain to deal with. So obviously, the moon is curving faster than the Earth as well. So there are a lot of things that make it challenging. Ray tracing can have some challenges getting over the horizon, getting over long distances. So we're working on enhancements to deal with that, getting over the lip of a crater and into a crater. So being able to do this in 3 dimensions, but being able to do it over the longer ranges that are required as well, and putting all of that together is what we're working on right now and the enhancements that we're doing. And then on top of that, the materials are different. So instead of buildings and well-defined materials for construction materials, a lot of times that we deal with in the private sector, whether it's indoor or outdoor, we're looking at things like regolith. And as I think was touched on a little bit earlier, it may be stratified, it's varying as it goes down, and it's very electrically transparent for quite a depth as well. And so you may get all the way down to bedrock, tens of meters below, and be reflecting off of that surface as well. So thinking of a surface model, you have to also be thinking under that surface in a much deeper, literally way than we have traditionally done on the Earth. And when you start doing that, you start thinking about scattering of things that are under the surface as well that you may not be able to see. So there's a lot to deal with there. And as Mike and others have pointed out, getting measurements and samples to see what's happening under the surface and how the propagation is working to validate our models, definitely very important. We do models because it's cheaper than measurements. You can do a lot of simulations, but you have to have those measurements as much as you can get to validate those models. So there's a handshake and a cooperation there, and that's clearly going to be a challenging part with the moon also.
Thank you.
Mhm.
And what about FCC perspective? How are we working to address these sorts of challenges? And are there any others that we haven't mentioned?
From FCC side, I agree with the panelists on the different aspects that they brought about the challenges, the multipath environment in lunar, and how we gonna getting some measurements. Glad to hear that you're already starting to get some measurements from in lunar, and how we gonna establish verification, validation processes that we are even again struggling to establish those processes for even terrestrial propagation models. In FCC, from my point of view, taking a step back, that always kind of we always as RF engineers, we're always trying to go directly to the solution. It would be beneficial, in my opinion, to take a step back and look what we are looking to solve this problem, the lunar propagation, by applying some system and engineering principles, and especially the verification validation model. That will help, I think, the whole community, especially those like FCC that they are not totally direct involved into this lunar exploration, to understand the use cases. And when I said use cases, it can be the short range, long range, but how this connected to the energotopology. How we are thinking that it's going to be in the short term, the communications on lunar. Then that will help us establish some requirements, which is important. It can be, of course, as the panelists mentioned, going to be line of sight. Then we need to certainly to understand the reflections from the lunar surface, the scattering and the reflections, diffractions from the nearby hills. We have another problem. We have a lot of graders in lunar. That's a very different environment than Earth. We need to understand that multiple effects. But we need to establish these requirements in order to understand what this should be an accurate model. Because it's a very broad terminology. makes a model accurate? It can be in different answers. We can have a different levels of accuracy. If we do that, then our accepted criteria, it can be like a mixed bag for me. And then we're gonna end up end up to have different models that we have to establish in order to meet the criteria. And then I give you an example, sorry for taking me too long. For example, we can have a very short computational programs like ILM now, right? That is going to compute everything in a millisecond. But then, as Greg mentioned, we can have ray tracing that it may take a long time. And maybe both, we made both computational models, it can be required in order to understand better the environment and then apply our knowledge to tune semi-empirical or even deterministic models. I'll stop here.
No, it's fascinating. Thank you
Yeah.
for sharing all of this with us. So we've talked about some of the challenges. We've heard the word multipath and scattering. I think for some of us who aren't in the weeds of lunar, when we think of these words, we do think of terrestrial models, and we might think of a dense city with buildings and signals scattering off these buildings. And so it's really interesting to hear about how this might relate in a lunar environment with regolith and signals below the surface of the moon as well. So I appreciate you all sharing that. One thing that you just mentioned, Chris, was kind of this concept that we could all be working on independent models. And I'm curious if there is a future in which kind of a standard model could exist, or global kind of efforts coming together. What sort of time frame, if you do think this is possible, do you think would be realistic for us working together? And who are the players that are keen to work with us on these sorts of lunar modeling?
Oh,
Chris,
wow.
I see you're off mute. So.
I would be remiss to my colleagues in the electromagnetics world if I did not point out that we have such a model already. It's called Maxwell's equations, and the problem is it's extremely hard to solve Maxwell's equations. This is why we have all these various families of models. Ray tracing, diffraction, empirical models, free space, et cetera, et cetera. These are all ways of solving or ways of approximating Maxwell's equations. So I think that could we all get together and create sort of the one model to rule them all, right? The one ring of propagation models. For years I've pondered this question, and I really believe that what might be more valuable is a family of models where we can say, for these situations, this is the best model to use. And Chrysanthos pointed out, we need a definition for what best means. What does it mean to be an accurate, trusted, high fidelity propagation model? And maybe for these situations, this is the model that should be used, and so on and so on. And I think that's where having spent time in the academic community, building a coalition of academics, of government, of industry, partnering with folks internationally to kind of come together in some sort of a forum where those decisions can be made, grounded in physics, grounded, with trusted measurement data, I think is the approach that would probably need to happen.
Any other thoughts here? Also see a question came in kind of similar, but possibilities for working particularly with entities like ESA or JAXA to obtain kind of validation for measurements they've taken. So thinking about that, wondering if that's realistic, wondering what timelines are involved there, and as we think about interacting with entities outside the United States.
Yeah, I can maybe talk about that a little bit. So I mean, I talked about the Intuitive Machines missions, which is, US NASA CLIPS program. But obviously there's, global interest in returning to the moon. We have a lot of partners under the Artemis Accords. And we have the ITU as a great forum for engaging with the international community. So for example, even just in terms of past missions from, the past year or so, JAXA landed their SLIM lander on the lunar surface. ISRO, the Indian Space Agency, landed their Chandrayaan lander on the lunar surface. And in each of those cases, there's varying amounts of data that could potentially also be of use in model validation, right? And we were talking about just how rare that actually is and how valuable every single opportunity to get data is from the lunar surface. So I think a very important part of this is, good coordination with our international partners. And as one possible example, I've been thinking that it'd be very beneficial to have standardized data banks in study group 3 or wherever it belongs, to be able to encourage our international partners to participate in that and submit the data that they've gathered, and just be open and be able to share every valuable little piece of data we can get from every mission that lands on the surface.
And just in case we have folks who are new to the topic joining, when you say study group 3, where is that organized?
Yeah, so study group 3 is under ITUR, the radio communication sector, and study group 3 is the group that focuses on radio wave propagation.
Thank you. And we've received several really fantastic questions from the audience, so thank you for those who are submitting them. Kind of tagging back on the ITU related question, curious if there are recommendations or reports addressing lunar propagation or modeling at the ITU.
Yeah, so I'll answer that a little bit, I guess, and then pass it to some other panelists. But yeah, there's a lot of activity right now in study group 3 related to lunar propagation, but primarily with the irregular lunar model that Billy presented on. And then I think ultimately we're going to have to start addressing questions like, whether we need a specific multipath fading model for direct to Earth links. I don't know if we touched on this a little bit already, but a lot of the activity, interest in going back to the moon centers on the South Pole. So there's permanently shadowed regions that are, thought, if not confirmed, to have water ice present. So, a lot of interest is going to the poles, and that, based on the Earth-Moon geometry, positions us in a location where any links back to Earth are very low elevation angle, and so we get a lot of reflections off the terrain and potential multipath fading. So it's another issue I think we're going to have to continue to investigate. But yeah, ultimately, I think in ITU parlance, a lot of these models end up as standard recommendations, and I think ultimately it would be good to try and push for the irregular lunar model, future models for multipath or any other effects, to wind up in that kind of format.
Thank you. Greg, is private sector participating in the developments of these ITU recommendations or studies that you're aware of?
I can't speak to others. I think we're aware of certain things that NASA's involved in, and we're using a draft recommendation on lunar materials, for example, and trying to certainly bring that in. We would be, of course, very happy ourselves to be participating. And just to go to what Dr. Anderson said, I think we very much agree that there are models for different purposes, and it is good to think about a family of models. That's how we approach things as well. And I think there are cases where maybe path loss is sufficient for something you're trying to understand, and there may be others where you're looking at multipath, which we've been bringing up, in part because the multipath could have effects, intersymbol interference. There could be things with the fading that impact communications that cause you to get less data throughput that could be important for someone who's interested at that level. And there may be other cases where someone just wants to generally bound in a level of interference and can use something simpler and faster, maybe propagating longer ranges. So definitely a family of models, I think, makes sense, and we're working to try to develop some things very focused on the 3D multipath. And like I said, we'd be happy to participate in ITU as well. We're trying to stay abreast of it right now, but definitely something we'd like to be actively involved with.
Fantastic, thank you.
I don't want to monopolize the time, but if I could jump in real quick, I just wanted to mention that as part of the validation activities that we have going on at NASA, we see engagement with our commercial partners like REMCOM. We also have a good relationship with ANSYS, using that type of ray tracing analysis kind of as the best we can do short of actual lunar data, right? Is a very good opportunity to do that validation. So certainly that's a big component of NASA's engagement in the ITU process as well, model of validation.
Would anyone else like to chime in before I move on to our next question? Alrighty, so we've been talking about measurements, validation techniques. I'm curious, and maybe if we've touched on this briefly, we could expand a little bit more. But what are the specific measurements that we need in order to verify and validate some of the empirical assessments that are embedded into the ILM?
I guess maybe I'll kick things off with a few thoughts. So I think Michael mentioned the knife edge diffraction, right? So the moon's a very interesting surface, right? Because it has not been subject to erosion from atmospheric effects and weather effects like we have here on Earth. So things seem to be sharper. The ground surface tends to be rougher or perhaps covered in dust or both. So the ridge lines are going to be understanding that diffraction over the ridge lines is going to be very important. Understanding the effects of craters. We tend not to have a lot of craters here on Earth, but we can have large craters, small craters, on the moon. Obviously, thinking, in lower frequency, HF, VHF, folks have talked about the composition of the lunar surface is going to become very important when we start talking about lower frequencies. So having a wide range of frequencies, from HF, all the way through millimeter wave, perhaps, or beyond, could be important. Understanding what's line of sight, what's beyond the horizon, what happens beyond the horizon on the lunar surface. Is it smooth sphere diffraction, or do multipath effects come into play? Short ranges, long ranges. I mean, I feel like I'm covering everything. It's sort of measure everything all the time, no matter what. But I think there's a variety of scenarios that I think are going to be important to validate some of the physics-based approaches in the ILM, for example, and then understanding things like multipath for the ray tracing and the 3D type models that are looking at the out of plane scattering.
Thank you. Anyone else want to contribute about the specific measurements?
Well, I think
Go ahead.
okay, I was just going to say, as Dr. Anderson was mentioning, that 3D multipath, there are a lot of things that we, of course, would be looking for in measurements. We're in discussions with Mike Zemba and looking to see what's happening in these missions, because unfortunately, unlike the Earth, we can't design an experiment as easily or ask for things. We have to sort of use moments of opportunity to see what's being collected and see what we can get from that. So, but anything that gives us more insight into the regolith and what's happening underneath the regolith. So if people are drilling down to look for ice and doing core samples, maybe also gathering information on the regolith and getting a better and better understanding from a scientific standpoint there. And then, of course, measurements, getting good data on where things are, how high they are above the terrain, where the transmitter is, what its antenna looks like, and the receiving as well. A lot of times when you're doing validation, you really need a lot of details of what the link is. And then, of course, recording enough data so that we can look at multipath can be challenging, because we need to understand what the multipath is, we need to get data with enough information to see how the copies of the signal and additional copies are arriving, what kinds of delays they have in the additional arriving copies of that signal, the multipath delay spread. So there's a lot of data that would be useful and interesting. In the near term, we may just be left with what we can gather from links, from, did they have coverage? Did they not? Can we sort of predict something similar and kind of do matching that way? But maybe in time we can help get more and more data to get to that level of fidelity, because ultimately that's what we're going to need to have good multipath models and good propagation models.
Thank you. Chris, do you have something to add?
Yes, kind of probably repeat what Greg and Chris already mentioned. But if I will look at this from the complexity of taking measurements, I think the first order is to take more measurements in the LOS environment. That may include open spaces, also includes maybe multiple effects, and that it will help us to understand the regolith, as Greg said, can understand the reflections and the roughness of the surface of lunar, since it's different from the Earth. I think that's, in my opinion, the first priority. We put it that before we move to much more complicated environments like the no line of sight. That also helps us to kind of say the same thing that hey, how is the propagation it is in on lunar, because the propagation really is the most important, one of the most important parameters in order to build your channel and understand the maybe the interference, like the time delays, that may cause intersymbol interference, but also may understand the extent of your links, because if the lunar surface provides us a lot of complexity of propagation, then maybe we have to create networks that they are not very similar to Earth. And especially since the atmosphere is not there, for example, going beyond of line of sight, there is no troposcattering. In ITM, for example, on Earth, that's one of the mechanisms to go beyond of line of sight. Now you may have to depend on multiple knife edges that on vertical plane that it may be not provide you too many losses for any to close any link, and then in that case you may have to depend on the multipath environment or some other mechanisms in order to have communication.
Thank you for that. So we've talked about kind of the current state of the models. And one thing I'm curious about, we've talked about more validation or efforts to validate. We've talked about collaboration at the ITU. Can someone expand upon like desired upgrades for the model? Obviously, we want to validate and make sure it's correct, but are there certain features based off where we are now that we would like to see included in the near term or the far term that you can explain maybe in more of a layman's or layperson's terms? And whoever would like to address this, feel free to jump in.
I can go first, this one. Sorry for the sequence, but I think we discussed a lot of the models already. But one thing, since we discussed before accuracy, one area that we maybe we can entertain is the as we said before, maybe we can have a lot of different models that we can try to validate and verify based on measurements. One thing in ITM, right, in ILM now, the diffraction, the knife edges that we want for long ranges beyond our line of sight, they are based on geometric theory of diffraction. And I'm sorry to become a little bit technical here. And the geometric theory diffraction is considers that the edges along a path, they are isolated. They are far apart. So you can determine the losses for each edge independently. And if you don't have too many edges between the transmitter and receiver, we know that is working. But it's a lot of cases the environment is not like that. And maybe even lunar in most of the cases is not like that. You may have maybe a lot of edges that they play a role between the transmitter and receiver. So what we are doing here, I think that that area of diffraction, that is also we are looking in the for terrestrial environments, it becomes a little bit more complicated. One way of resolving the multiple knife edge is to use much more computational programs, like by integrate the sequence of edges, like how Vogler and Bertoni models do. That will give us some reference, what we should expect the losses. Then after that, it maybe give us an opportunity, if we understand that, to build some more simplified models. It's still geometric theory diffraction, isolated edges, maybe still apply if the specific criteria are there. But maybe we can build also more simplified formulas from Vogler and Bertoni that allows determine diffraction losses that you have edges that they are similar with each other, but they're in sequence. I think that's an area that we need to, in my opinion, we need to improve in the ILM and also for terrestrial models. And I think the other area, it is for me that is one question that we didn't touch right now. We know in lunar there is sunstorms. It's a phenomenon that maybe we have in certain places on Earth, but I'm not sure how the impact, that this variability will impact the overall connectivity. So I think we should build a model to determine that, that variability due to sunstorms and any other environmental effect.
Thank you. So just a reminder, the questions on upgrades we'd like to see. And I was curious about how variability is taken into the model as well. So sandstorms is something that can change over time. So maybe to ask, but also to avoid two questions at the same time, ask the panelists either about upgrades or how we're treating variability. Maybe they go hand in hand.
Yeah, I could comment a little bit on how we're doing in our research. Now, this isn't specifically about the ILM. This is more about what we're doing, which is ray tracing based in our SBIR. But the first, the lunar dust, the exosphere that's created in the lit regions of the moon, we did look into that, and I think it appears, at least from what we have seen so far, that the propagation through that exosphere is not hugely affected until you get to very low frequencies, but the ionized dust can collect on things like antennas. So we also looked at antenna effects and whether there could be losses in the antennas. So the starting point for all of our calculations is always that antenna gain pattern, the VISWAR, the impedances and the losses, and that's where we anticipate there will be effects. So capturing that could be the first step of putting in those effects, that when you have dust, if it's on your antennas, what impact will that have? And all the other things we've talked about, improvements for curved surfaces of the lip of a crater and diffracting over that is something we're looking very closely at. So to Chrysanthos's comments on diffraction is very important. There's very different aspects to the diffractions. For example, getting down into craters, which are going to be very important for communications, figuring out where to put relays. Then that's an area that requires enhancements in ray tracing to be able to capture well and computationally efficiently. So we're working on those things too. And all of these things, obviously there could then be impacts too with the ILM. If they were to factor in antenna patterns, they could be looking at losses from dust as well, maybe augmentations to their diffraction models to account for the shapes of the terrain. And of course, the variability, when you start thinking about things like diffuse scattering from subsurface rocks, as an example, we're not going to know where all those rocks are. So it starts to become a statistical problem, and then that becomes a problem with a lot of uncertainty in your answers. And you need to start thinking statistically about how you're going to handle that variability to your channel and to your propagation. So those are at least some of the things that we're looking at in the research that we're doing.
Thank you for that. Any others like to contribute before I go to the next question? All right, well, I'm going to take a question that we've received from our audience. So maybe Greg, you could kick us off with this too, but Shackleton Crater is 4 kilometers deep, 20 kilometers wide, bigger than Manhattan. How important is capturing accurate ground bounce and backscatter as astronauts are in motion?
Yeah, that's a great question. It's if you're just looking at losses, you may overlook some of these multipath effects. The first one, though, of course, it's very deep, and in the terrain data that we've looked at, it actually curves down very rapidly as well. And so it's you very quickly can get into shadows as you're going down on the near slope. That's very interesting to see that. And then, of course, when you have multipath, some of those effects are shadowing. You can have ground reflections causing cancellation, just like in terrestrial surfaces, but the material properties, of course, are very different as we've talked about with regolith. Then when you are looking at multipath, one of the reasons we are so interested in multipath, and we're talking about that with the channels, is because if you have communications, there are certain things that are put into 4G and 5G to try to deal with a multipath delay spread. They can handle a certain amount, but if that delay spread gets too great, you'll see that if you just do a rough estimate of power and signal to noise, you might think you can get a certain level of data throughput. And when you start factoring in all the delay spread from all the copies of your signal and the intersymbol interference that they cause, suddenly your throughput can drop very rapidly. So you can have someone go over the lip into a shadow, lose connectivity to them. You could have them go down in a place that's not in a shadow, but lose connectivity because of fading or have their data rate drop very rapidly. So trying to understand that is very critical. And the crater is maybe one of the most interesting cases because of the shape and the rapid shadows that we hit and all the multipath that we get from all the sides and far sides of the crater. And then, of course, on top of that, antennas on when we're dealing in urban areas or in terrestrial communications, we're very used to having cell towers creating cells where we may have cell towers in many positions around us. And on the moon, there's a good chance that we'll be moving this way and have all our communications in a link in that direction. And so even the body or the vehicles, it might be more important to understand how those are going to affect and even shadow a device that's immediately on you and make sure that you're getting enough diversity in your antennas and things like that to get communication back to the small number of links you may have. So those are some of the things that come to
Thank you.
mind.
Yeah.
Would anyone, oh, thanks, Mike. Go for it.
Yeah, sorry, I was just going to jump in and emphasize the importance of that multipath and how we can capture that in the modeling. So NASA's currently, doing a lot of analysis and looking at different network technologies for surface wireless. Different versions of Wi-Fi, Wi-Fi 5, Wi-Fi 6, different 3GPP protocols, 4G and 5G, historical technologies like NASA's space-to-space comm system. And each of those have different amounts of capability to be able to deal with that multipath environment, different subcarrier spacings, different cyclic prefix lengths, things like that. And so I think being able to accurately model and at least understand the possible range of delay spreads that we're going to see on the surface is very important in making those selections and understanding how much can we rely on something with maybe a shorter cyclic prefix lengths to actually be able to avoid intersymbol interference from distant reflections, and how much do we need to push to move to more and more capable systems to deal with that as we're seeing distant reflections off of a distant crater wall or something like that.
Thank you.
Yeah, and if I could maybe jump in for a second here, I think this illustrates the comment that I made earlier about perhaps considering a family of models rather than one specific model, right? Because we've talked about, with the crater example, we've talked about a couple of use cases. One is for coverage or interference planning, what is the received power at a particular point in that crater? But also for designing comms links, what does the delay spreads look like? What does the intersymbol interference look like? What does the multipath environment look like? And I'll even throw out there perhaps a high mobility scenario. So we've talked about things moving around. Right now they probably move pretty slowly on the moon, but perhaps one day things will move with significant velocities. And now you introduce statistics that may be time varying. And so understanding those kinds of scenarios is important, again, for designing comms links, understanding patterns of use or potential for signal enhancements that might lead to odd interference events, for example. So again, I think the use case is really important, and perhaps thinking there may be more than one model that is needed given the scenario that's under consideration.
Thank you for that. Chris, did you want to add anything before I move on?
I agree. Just to add to Dr. Anderson use cases, and I think Mike implied that they tried different networking. For example, just to give an example, what we're talking here as a use cases, let's think that the robot is in the grader. Where is the antenna and the other base station that it needs to communicate? If it's outside of the grade, then certainly at that point you don't have a line of sight. Totally you depending on diffraction and backscattering in order to reach to the antenna. It's a very different model than if you're considering a use cases that you're inside in the grader and then you have some UAV that hover over the grader and becomes a middle point that communicates with the robot, and then the UAV retransmit the information to somewhere else. So in that case, you have line of sight. Then you have the issues with the multiple paths that you may be cause you some time delays and intersymbol interference. But this is two different models, and the distribution is different, because in one you have line of sight, it's going to be region, the other one not. So we need to take all this account, because it's not just to attempt to predict the median. The key for me is not to figure out what is the mean and the RMS. It is really to get exactly the distribution. If you don't get the correct prediction losses in a distribution format, then we're not going to know what is the 99% confidence or even higher to ensure connectivity. And I think we need to take all this stuff in consideration.
Thank you. So we've received many questions, and they're fantastic. So I want to take some time to address more of these. One is just actually taking a step back and thinking about the use cases that the ILM considers. So we've talked about astronauts. We've just heard about unmanned vehicle overhead, UAV. Potentially, we've talked about what Greg was mentioning, moving in one direction, but your communications network is behind you. Are there certain use cases that the ILM is focusing on? Or are there some that we are considering at the ITU level that we haven't really explained here in plain language?
Yeah, so I guess I can maybe kick off the discussion. So that the ILM, again, being derived from the irregular terrain model, has two modes. So it has a point-to-point mode. So you have a transmitter at point X, you have a receiver at point Y, you have information about the terrain profile and the surface material makeup in between, and it's going to compute path loss from those 2 points. And then it has an area mode, which takes into account statistics about the terrain roughness, and again, some more general parameters to make kind of a general prediction using some variability statistics. So those are the two use cases. Again, sort of a general area. If I've got some general information about the environment, can I say something about what does the coverage look like from a transmitter in a particular location, or doing a point X to point Y propagation loss computation. Again, multipath is not part of the ILM.
Anyone else? Go ahead, Greg.
I was just going to say, I guess you could think of, depending on what you meant by use cases, you could think of, there are several that have been defined, things like intra-vehicle, which may extend out with a local area network. So that might be more like a local Wi-Fi. There are some communications between vehicles, which may go out to, say, 10 kilometers or more. We've been talking a lot about surface to surface, which could include EVA to rovers, maybe some of the robotics things we've talked about, back to a habitat, things that might go out to longer ranges. And then of course there is the surface to orbiters. So when we were just talking about motion and mobility, that's another case. If we're worried about high velocity, we may have orbiting satellites, and especially in cases like a crater, if there's any communication into a deeply shadowed area, you could have some Doppler and some other things, and a change in link. So definitely a lot of different things, but those are maybe some broad kind of use cases in terms of the kind of communications that we anticipate that could require us to look at this problem a little differently for each one, and think about what the main issues are going to be for each of those.
Thank you. I'm curious, we've talked and we've used the word general a few times. Could the ILM apply to other celestial bodies or rocky planets? Moons? You want to take that one?
I'll start. I guess, I mean, obviously, it depends on how similar the other planet is to the lunar surface. So for example, maybe another rocky body without an atmosphere, like say Mercury or Pluto or something, you could potentially adjust the characteristics of the terrain to match the characteristics of the other body, and potentially some of the remaining physics would be similar. I think if we talked about applying it to, say, Mars with a thin atmosphere, then we'd have to, do more legwork to investigate how do we translate our atmospheric type phenomenon to a model for a planet that's got an atmosphere.
Thank you. Let's see.
I guess I could comment quickly on that, not about the ILM specifically, but again, in the kind of research that we're doing, we do see a lot of uses for some of these same capabilities that we're trying to do for the terrain for the moon as being useful for terrestrial applications and being useful for Mars as well. But as Mike Zemba pointed out, there will be differences in other phenomena in any model that you have to pay attention to. If obviously, if the planet has an atmosphere, there's a whole new study there to figure out what that atmosphere looks like from a propagation standpoint.
Thank you. Any other thoughts? So one question, we talked about challenges with the model itself. When we think about going forward, we've talked about global cooperation or coordination. What are some of the challenges you foresee, if any, in kind of progressing these models long term? And also, like with that, if there was one thing that would kind of make your day-to-day easier, what would that be outside of just having perfect measurements for whatever you're trying to validate?
I mean, I guess maybe I'll kick off. What are the challenges going forward? So every propagation paper that I've ever published in the academic literature, the first round of reviews has always come back with, well, we'd like to see you have more data. It didn't matter if I had 1,000 data points or 100,000 data points or 500,000 data points. The reviewers always said, oh, you need more data. I think the big challenges we've talked about is data, and it's going to be getting quote unquote enough data. What is going to be enough data to satisfy the international community that there is enough data to actually validate the models that we're discussing.
Yeah, I can jump in just to add that I think in terms of the need for a lot of data, one of the concerns I have is how much variability we observe from location to location. So, we're planning different missions, and they may all be around the South Pole, and we may expect very similar electrical characteristics, but we may see, for example, very different, different variations in the depth of the regolith layer, or different variations in how the local topography around a region is contributing specifically to the multipath environment. So I think it's going to be a challenge to understand how we can have a generalized model and then best tailor that to specific locations that missions are planning for at any given time.
just to add a couple of thoughts here, it's overall in this community, we know how difficult it is to make tools to be acceptable. And one of the reasons, as we mentioned before, is that we don't have very good yet validation verification process that would enable us to determine the validity of some of these models. Putting that together to be more acceptable in the international community, besides creating some more models, they need some of these models to be a little bit more towards to deterministic, that will allow us to tune them a little bit easier than the ITM that is a semi-empirical, or ILM that is semi-empirical models. And I'm saying that because one technique that we didn't talk too much that we may apply to the propagation model is machine learning, all right? If we have some measurements and then we build some deterministic model that is sufficient to understand and characterize the interactions of the rays, like reflections, diffractions, and scattering, then we can use the machine language to tune this model. And I think if we take that kind of little bit direction, that maybe make it things a little bit easier to be acceptable. And I didn't see too much in this area. I think it's too early. I don't know if Mike and NASA will publish some of these measurements, because you need the measurements in order to apply machine learning. So hopefully, as we get in there and have a little bit of measurement, especially in a short range, in line of sight that and characterize the multipath, that will be a huge step ahead, in my opinion. A small step, but a big step. Because then we can extend that knowledge to no line of sight.
Thank you. Okay, completely kind of other direction based off a question we've received. Just general overview of federal support for these efforts and how that may evolve with time. Curious if anyone can share with us how funding supports lunar propagation models currently. We've heard, Greg, you said SBIR. We hear NTIA, NASA, FCC representatives on the panel. So yeah, could someone help us understand this?
Well, I could just extend on what I said before. We have over the years gotten SBIRs and other contracts to do a lot of propagation development for the DoD as well, and now we have some with NASA. So we also do, as you pointed out, we do a lot of things with industry, sometimes contractually, but sometimes we sell products and then we tune them for the market to try to make sure they're meeting the needs. So we do a lot of different combinations, but at least for us, the lunar it's a new and unique opportunity, and we're obviously getting very grateful to have some work through this SBIR process with NASA, and that's been very helpful for us to be able to start this research, because until without some sort of government funding, like a lot of things when you have a new venture like this, until there's an industry up there, you're not going to have funding coming in that route, and so you need some R&D up front, and so that's been very helpful for us to help move our models forward, and that's what we're involved in right now, to try to do the best we can for this new and interesting environment.
Yeah, I will mention too. I mean, we've had great success with the SBIR with REMCOM, and that's the solicitation for next year's SBIR proposals is going out again. So for anyone online to whom that may apply, if you're interested, there will be another call for SBIR proposals, and it's specifically under the Lunar 3GPP subtopic, but then one of the callouts there is a specific need for modeling and simulation capability. So there's a potential source of funding for future industry partners. And then otherwise within NASA, we do have good support from SCAN, which is the Space Comm and Nav group within NASA, to continue these lunar propagation efforts. Over the next several years, to engage with ITU to try and consolidate the mission data that we're getting back So we expect to continue that support for a while.
Right. So I want to note that this panel wasn't intended to focus on spectrum. One thing I'm wondering about, and if we don't have thoughts, we can defer this question, also came in through the Q&A, is just about when we are doing these studies at the ITU and we're using certain frequency bands, whether what is the general consensus on the frequencies that are being used and targeted for lunar missions and for lunar modeling, or are they generalized to cover a wide range of frequencies? Does someone feel okay to take a pass at that one?
So I can comment. So especially with regard to leveraging terrestrial development, we're very interested in how we can utilize Wi-Fi and 3GPP technologies. And so a lot of that hardware is designed around specific bands. There's a whole broad swath of 4G and 5G bands on Earth. But I think given that, we'd be happy with whatever spectrum negotiations shake out for a band within that range. But I think being able to target bands.
Sorry, could you repeat the range you were saying that you'd be happy with?
So basically anything that the 4G or 5G or Wi-Fi technologies operate in. And so 4G, I don't even think I know the entire range. There's a whole list of different bands, but low or upper 700 megahertz up to I think 6 gigahertz. And then there's the FR2 band that's up at the Ka band in the 20 gigahertz range. But for 3GPP, we're primarily focused in FR1. And then for Wi-Fi, it's the 2.4 and the 5 gigahertz, right?
Okay. Anyone else want to talk about spectrum?
Yeah, I would just say that the solutions we're working on are, to your question about are they general or specific, they're generalized enough. We are focused, of course, on several hundred megahertz up to, perhaps as high as 100 gigahertz, just looking to the future. 4G, 5G, and 6G keep pushing upwards, but we try not to be band specific. We're not developing empirical models. We're developing models based on first principles. So as long as all the inputs are accurate, then the model should be good to an extent. And then every technique that you have, of course, is making assumptions. As Dr. Anderson started to say about Maxwell's equations, there are assumptions that are being made on starting with Maxwell's equations, and those assumptions have limits to an extent. But for us, it's a smooth range from a lower to an upper bound on the frequencies, and we're not targeting specific bands. But of course, our demonstrations and the things we're studying are focused. If it's Wi-Fi, then we'll be in the Wi-Fi bands. If we're trying to demonstrate a concept, or for 5G, we may go up into FR2 and go up to higher millimeter wave bands. So that's kind of how we're focusing on these things.
Thank you. So kind of approaching closing of our panel, I'm curious if there's any sort of questions or topics we haven't touched on that you would be remiss to not bring up, or any sort of exciting events happening in the near future for modeling in general. And I guess, Mike, before you jump in, I'll follow that on with, if I'm an audience member, I want to stay involved in learning about the progress with lunar propagation modeling. How is best for me to do that? How can I stay involved even if I'm not working with you all in the day-to-day?
Yeah, sure. So I was just on the subject of upcoming opportunities. The one thing we haven't mentioned so far that I'm personally very excited about is on Artemis 3, which is the intended first crewed landing back to the lunar surface. There's also a comm demonstration plan for that, where they would use a similar system for the crew a similar system to the IM2 demonstration with the 4G LTE hardware. So the crew will go out and collect measurements and give us another opportunity to get data from the surface. So I just wanted to mention that as another exciting upcoming opportunity, although that one is still a couple of years away at the earliest. And in terms of staying engaged, I would say certainly anybody, feel free to reach out to me. I don't want to speak for the rest of the panel, but I'm sure they're also similarly very open and interested in coordination. And then the ITU also is a very great opportunity to come together as a forum and work together on these things.
Yeah, and I would just say, of course, people can reach out to REMCOM. As we are developing new capabilities, we're putting them into our models. So we do have a beta that can load lunar terrain, for example, and we do have people using it. So you could keep abreast of what's going on just by, staying in touch with us, and we can show you what we have. We have a lot more coming, but we do have things, and it's going to be an ongoing process. So we're always happy to have people involved with us. And we work with academia, industry, government. So anybody's welcome to stay in touch and keep abreast of what we're up to. I
Thank you.
think we're very excited about this. Obviously, everything that's going to be happening on the moon, I'm sure everybody is. So I would say when your point about the upcoming excited things, I'd have to echo what Michael said. It's the missions that are coming are the real exciting things. So that's what we're looking forward to.
Dr. Lomayer, I would like to thank NTIA again for inviting me here today. From FCC, we have a small team that we're RF propagation experts, but we're looking to continue our working closely with NTIA and NASA under Study Group 3 on Lunar. We're working for other models, terrestrial models like mean band with NTIA, and I think that kind of these very complex models that you can have to look at them from many different use cases. It needs a very close collaboration from the federal government and industry and academia in order to know what not to just only to know what each other does, but also share information, and that would also help us to come to better conclusions what models are applicable for different use cases.
And Dr. Anderson, anything else to wrap us up?
I don't think so. I mean, certainly, Billy shared the link for downloading the irregular lunar model, and certainly you can follow along that site if you want to stay abreast of any updates that we make to that.
All right. Well, thank you all, and I'm going to hand it over to Jennifer.
Thanks so much, Dr. Lohmeyer, and thank you very much to our panelists. I think that was a great conversation. And I also want to thank our audience for so many questions. I was really pleased to see the engagement, and I think that shows just how important and exciting this area is. And we're really looking forward to seeing what happens, especially in real life. As folks mentioned, the missions are really where we want to go. So I'm hoping that everyone in our audience will continue to follow our what's going on in this area and get actively involved. But before I go, I do want to say thank you, besides, of course, to Sarah Morris, Billy Kozma, Dr. Lohmeyer, Michael Zamba, Greg Skidmore, Chris, and Chris. I want to thank some of the behind the scenes folks, Paul McKenna, who's with ITS, and actually when I joined NTIA a few months ago, he was the first person who came up to me and said, we should really do a workshop on this. So it's Paul's idea and his passion for this issue that brought us here. And then behind the scenes, we have Eric Rosenberg, Zoe Mecca, and John Alden, who have helped pull this all together. So with that, I want to thank, of course, our panelists and speakers. I want to thank our audience and look forward to seeing the continuing great work on this. Thanks so much, everyone, and thanks to our audience. Take care. Bye-bye.
Thanks.